All right, thanks. I'm going to talk about parallelism in SOFA. So is everyone okay with what parallelism is? Okay,
Yes.
so I'll start right away with presentation of what are the different possibilities that are available in SOFA in order to parallelize things. Because you will see that there you can parallelize different things. So I'll start with the task scheduler. I will present this. Usually when you want to compute things in parallel, you need to create threads, and creating threads is expensive. So you cannot do that if you need to create threads, I would say, a large number of times. So if you have like a finite element code, and for each element you want to create a thread, that would not be possible because threads are expensive to create. So that's why we have a thread pool. It's a common pattern that creates a thread at the beginning of the lifetime of the pool, and it uses a task queue and will use it to execute tasks. So the threads that are in the thread pool will wait for new tasks coming in the queue, so that you don't create threads when you need to compute a task. They are always there, and they are waiting for tasks to be queued. So you don't pay the overhead of creating threads. However, you pay the price of managing the task queue, but that's better than creating threads. And this thread pool in SOFA is called the task scheduler. So, for example, this is a C++ code that uses a task scheduler. This is in the free motion animation loop. First, we declare a task status, and we will provide it to the task scheduler when we want to add a task. Task is here. Do you see my mouse? Yes? All right. So the task is here as a lambda function. And in this lambda function, we will compute the free motion.
What is the lambda function?
The lambda function is an anonymous function. You can have, so here, instead of the lambda function, you can have a function pointer or a functor, but in modern C++, usually we use lambdas. It's much more convenient. So it's basically what is a task and a definition of the task and what will be executed in the task. So a lambda function is an object, and it can be stored, and it can be copied, etc. So here you see that this lambda will be stored in the task queue, waiting that a thread will be available and can execute it. So here we add a task that will compute the free motion, and right away we will continue to execute the next instruction, collision detection. So we don't wait that compute free motion is over, because compute free motion will be executed in another thread, a thread that belongs to the thread pool. So compute free motion and collision detection will be executed in two different threads. And this one, collision detection, is executed on the main thread, the one that executes so far. And the last line is to synchronize threads. So we want to say to all, to some threads that we want them to finish before continuing. So here we use the status, the task status, and we say that we want to wait until compute free motion is finished. And then we continue. Is that okay?
Can we ask a question right here, Alex?
Yeah, go ahead.
Cool. You mentioned that the collision detection function here is going to be called by the is going to be handled by the main thread, right?
Yes. Yes.
Does that mean by default that let's say that the line number 9 does not exist, that the main thread would be just like waiting the all other threads to end until the work until done the function is called to get back to its main task on the main thread on the single thread, or what does it do, the main thread, while all other tasks are actually distributed?
It's just waiting. It's
okay.
stalling.
Okay. Okay, thank you.
Yeah, it cannot go. It cannot do anything else. It's just wait.
Okay, cool. Thanks.
And you don't want that. Actually, you want. In multi-threading, you don't want threads to wait because it's you could do more instead of waiting, so you want to avoid this situation.
But it means that the task you give to the main thread, you need to be a bit cavalier, like managing properly the amount of work you're giving to the main thread, not overloading it compared to what is done in the other threads, and the inverse way around neither, like to give a very simple task to do and then keeping it waiting, right?
Yeah, here you have only two tasks and you expect that they will take about the same time.
Okay.
That would be the ideal situation.
Okay. Thanks.
Quentin?
Hey, Alex. Just a quick question because I'm not, but maybe it's just a simple one. So you're basically saying that compute free motion and collision detection will be running at the same time because on different threads, correct?
Yeah.
But don't the collision detection need the result of the compute free motion to and this is handled by the parallelization?
No, actually, in this case, in the case of the free motion, you don't need the result because
in fact, we are using not really collision, but proximity, and it's based on the position of previous step.
Oh, I see. Okay. So the position computed with compute free motion will be used on the next iteration.
Yeah. In the next step, within one time step, there are several things to be computed. The information computed by the compute free motion will be reused later on in the same time step. Yeah.
Okay, super.
But not by the collision detection.
Makes sense. Thank you.
All right. So you have seen that in this case, we have only two tasks that are computed in parallel, and there are quite heavy tasks, and we have only two. But now, let's say that we want to compute many small tasks. For example, on the right, in the code, we have an example of finite element code. So when we want to compute the force on the nodes, on the vertices of the mesh. So first we want to iterate over the elements of the mesh, and in this on every element we will compute a force, but it is computed by elements, and then we want to dispatch the result on the vertices, but it's not here. It's not here. The example will be shown later. But let's say we just want to iterate over the elements. So for every element, we add a task to the task pool that we want to compute the force inside the element that is visited. And so there will be a task that will be created for every element. And on the last line, we just say that we want to wait until all the tasks are finished. But if you do that, I mean, you can do that, but you will have a strong overhead by creating a large number of tasks and by managing the tasks list. So every time a thread is actually waiting for a task in the task queue. It sees that a task is available, you will take it, execute it, and then start to wait until there is another one. And every time it does that, and it does not really have to, but this is how it works. So there is a strong overhead if you have many tasks, many small tasks. So this is not really the way to do if you have this situation. So this is this is the situation that I described. Here you have let's say 3 threads, and every time you have a task, you have a small overhead, and in the end you accumulate all the overheads, and it's really not optimal, and it will take some time for nothing, because it does not compute anything. It just waits or managing the task list. And this is the optimal pattern, I would say. We have 3 threads, and we have only one overhead, and then we execute different tasks. So I will show you how we managed to get there. But before that, I want to have a little reminder of some basic C++. Because I want to talk about the containers library, the iterators library, and the algorithms library. All of that will be useful to present the solution of my many tasks problem. So this is a basic example. You see, I instantiate a vector. So it's a dynamic vector. You can modify its size and add and remove elements. Then I access to iterators of this vector. I want to get the beginning and the end iterators. And then I will use an algorithm that is in the algorithm library, scfind, This is basically just to find an element inside a container, and you have to pass two iterators, usually to every algorithm, beginning and end in this case, and the 4 is the value that we want to find. The result of a find is an iterator, and if the iterator is the end iterator, it means that we have looped over all elements and we haven't found the element. So this is what we do here. We detect if the element is found or not. So almost all algorithms are based on iterators with a beginning and an end. And begin and end does not have to be really the beginning and the end of the vector. It could be intermediate iterators if you want. The goal is to define a range between the beginning and the end. Is everything okay about containers, iterators, and algorithms? Are you all familiar with that? Now I will want to present the ForEach algorithm. It's also in the standard library, in the algorithm library. So ForEach is just an algorithm that will apply a function to every element between the two iterators. So here in line 9, I just say that I want to apply this function, this lambda function, to every element of this vector. And what this lambda function does is simply incrementing the value of the element. So if I do that, the result will be 2, 3, 4, 5, 6. And this is what I print here. For every element of the vector, I apply this function, and this function simply prints with stdcout the result in the console. And here I applied a reduction. I want to compute the sum of all elements. So I prepare the result here. It's equal to 0, and I capture the variable in the lambda so that I can use it in the lambda content. And I just say sum is incremented by the element of the container. And then I print the sum. Yeah. Is it okay?
Yes.
So the possible implementation for std4h could be that it could be because every compiler or every standard library has its own implementation, but it could look like that. So this is just a loop over all the elements between first and last, and we apply f. F is a function here, and it's a template parameter, so you don't know what it is, but you just know that f can be invoked. With an element of the container as a parameter. So unary function could be It could be a lambda, it could be a functor or a function pointer. Yeah. And now I want to introduce ForEach, but the parallel version. Can anyone spot the difference between this code and the previous one?
Line 10.
Line 10, yes. What is going on here?
It seems like you're specifying a new parameter, which is the type of execution, which seems to be parallel.
Yeah, it's called an execution policy. So this is a new parameter here. PAR means obviously parallel, but you have also SEQ, like sequential.
Which is, I guess, the one by default. If you do not give this parameter, I guess.
Exactly. So if I do that, I say that I want to execute the function here in parallel over all the elements of the vector. This is really simple, actually. You don't change a lot of the code compared to the previous one. Can anyone tell me why I did not add the parallel execution policy to the other ForEach?
I'm sorry, can you say that again?
Can you tell me why I did not add the parallel execution policy to the other ForEach, the lines 11 and 15?
It's not efficient. Parallel.
Well, even line 10 it's not efficient. We have only 5 items in the vector, so it's preferable to execute it in sequentially.
There is a remark of Damien, right? Do we want to print out of order?
Yeah, so 2 things here in line 11. You don't know the order of execution. So it means that 1 could be the first element visited, but 4 could be also the first element to be visited. And you won't have the same results in the end of line 11 compared to the sequential execution. So it's called a race condition. And on line 15, you will have a data race. It's a bit different. It's you will have different threads trying to write in the same variable at the same time, and you cannot do that. So you have a data race, and it could end up with a crash, simply a crash. So this is just a toy example, and if you want to do, so usually you have in situations where you have a race condition or a data race, and you will need some techniques to perhaps synchronize threads or acquire a lock on the threads so that only one thread is able to write and not the other.
Is that correct, Alex, to say that there is basically 3 things that can be like a condition not to use or not to use parallelism? It's the race condition that you mentioned, the concurrent access on data, and I guess then the performance depending on the the task amount and the complete, how complex is the task to be performed. Is there any other cases? Because here I see two cases which are I would have said the main issues with parallel tasks. If you don't think about like what you are actually parallelizing, do you think about any other problems or conditions where it would not be appropriate to use parallel approach?
Rate condition and data race are not, I would say, a criteria to prevent the parallelization, because you can always try to find another algorithm or a different pattern to execute, so that you avoid this situation. But usually it involves, like I said, thread synchronization, and this could be expensive. You waste some time, and it will affect the performances. So you will have, that's how you don't have the expected performances. If you have like n threads that could be executed in parallel on your computer, if you have threads synchronization, it does not mean that you will go n times faster, because usually algorithms are more complex than that. And and about your other point on the performances, yes, sometimes it's not preferable to execute in parallel, because I don't know, you have a small data set, like in this example, and it's better to execute it in sequence. Other than that, I don't know if there is another situation to.
I was just asking if you were like just like that thinking about other cases, but thank you anyway.
I don't know like that. Need to think about it, but I would say this is it's already quite complex. Only giving these three criteria. All right, so why don't we use parallel algorithms in SOFA? We could, but it's implementation specific. So it means that if you change your platform, if you execute the code on different platforms or different compilers, you will not have the same implementation. So you don't know what is going on actually behind the ForEach or the parallel algorithm. So, for example, Microsoft does not implement the ForEach the same way than GCC, for example. So you don't have any control on what's going on. You don't know if a thread will be created for your algorithm. So if, for example, I don't know how it is done in GCC, but in GCC, let's say ForEach creates a thread for every element, so you will have a stronger overhead. And lastly, compiler support is a bit of a problem. So what I presented here is supposed to be introduced in C++17, but in practice, all compilers do not support all the algorithms. It may basically the case at the really beginning of C++ 17. Now there is a strong support for all major compilers.
Alex?
Yes.
For the thread creation overhead, on the example you took the fact that you have, for instance, in a force field, you create a thread per element.
Yes.
But now we imagine that we keep this thread open because you in fact you reuse your force field over and over the steps of your simulation. So is it like the cost of maintaining like a thread open, is it something negligible or not? You see what I mean?
So you want to use a thread pool to do that. No, there is no really some cost of maintaining a thread alive. Actually, once the thread is created, the main thread does not really care about the other thread, unless you want it. But
And you can have as many threads open as you want, or is it?
there is a maximum number that is very high, so you will not get there. I know that it's maybe like 60,000 thread, things like that. But you will never create so many threads. Usually you create as many threads as you have the number of cores in your computer.
Okay, thank you. Hugo has a question.
Yeah, it's actually in the following what you just said, Christian. Then, if we take the example of domain decomposition, what you already introduced and start looking at, Alex, and with the remark of Christian, would that make sense, like to at the beginning of the simulation to create a number of threads dedicated to domains, and then reduce the costs of, like, recreating those threads at each time step or at each force field, and instead of that, like keeping them waiting and just reusing them straight away, as long as you consider there is no topological changes, it would be like optimal.
Yeah, that's exactly what the purpose of the thread pool.
Okay, cool. Okay, I did not know the thread pool was actually like keeping in memory how many threads had to be created and keeping them waiting. I thought, like, when you were doing the work until done, then when you were making this synchronization, it was basically killing everyone.
No. The pool keeps the threads alive.
Okay, sweet.
Until the pool is destroyed.
Okay, thank you.
Okay, so now I will switch to a parallelForEach implementation that I did in SOFA. So I introduced basically two functions, and this is very similar to what we have in the STL library. We have a parallelForEach that takes a task scheduler, first and last iterators, and the function to apply. And a second function that takes a range. I will go back to it later. It takes the same parameters, but f is a bit different here than here. I will explain it. If I go back to the first implementation, here is an example of how to use it. Let's say I generate a number of integers in a vector, and I want to do the same task than before, just incrementing every element. I call the parallelForEach. I give it a task scheduler, begin, end, and the task to apply. So this is very, very similar to the STL. But here we know that what is going on. We know that we use a task scheduler so the thread pool. Yeah, and it is portable. So the result won't change, or the algorithm managing the threads won't change in the back of this function. And here is an example for the parallelForEach range. This is a bit more complex, but it solves the situation that I presented earlier. This one. So every time you create a task, you have a small overhead that accumulates, and we don't want that. We just want one small overhead. And for that, we will use the parallelForEach range. What this function does is creating a number of tasks that is usually less than the number of elements in the container. It is corresponding to the number of threads in the thread pool. So let's say I have 3 threads. The optimal situation would be to create 3 tasks, and in each task we will do a loop executing a task on each element. So it's hard to explain, but if I do that, I avoid the overhead that I presented earlier. So instead of doing one task per element, I do many tasks in a loop, and this loop starts and ends in a range of the container that is defined by the function. So you don't have to know exactly where it starts and where it ends. It computes it automatically based on the number of threads in the thread pool and based on the number of elements in your container. That okay? So if you have 3 threads, usually you will have 3 tasks, and in each task you have a loop over the element of the container. So it's a bit more complex than this version, but this is to avoid overhead and improve the performance. This is an example a bit more complex. That is a real example in the FEM code. We have the parallelForEach range here that takes the task scheduler. As usual, we have the beginning end of the container. And here we have the lambda function that will be executed. So this one is a bit longer than what we had previously. So here from line 8 to 14, we prepare the data. So you see that I want to pre-allocate the result here based on the distance. So distance is actually the number of elements that will be visited in this loop. So here we go with the loop. We access to the element, and then we do a bunch of computation until we get the result here, and we push it back to the result, vector. And then it's like I said earlier, we compute the force in the element, but then we want to dispatch it to the vertices. But we cannot really do that in parallel, because one element in a thread can affect a vertex that is maybe accessed in another thread, because two adjacent elements can share a common vertex, and two adjacent element could be computed in two different threads. So you have a data race here, and to prevent that, I added a mutex here. And when a thread is executing this line here, it says, I want to acquire the mutex, and all the threads that will end up in this line will see that one thread has already acquired the mutex, and it will wait until the mutex is unlocked. So when you see this code here, this loop that dispatch the force from the element to the vertices, it is executed on only one thread at a time because of the mutex. And when the mutex is released at the end of the function, another thread will acquire the mutex and will be able to execute this function. Is it okay? Yeah. All right. So this was a presentation of what you can use in C++ to parallelize your algorithms. So it could be easy, but if you have a data race or race condition, it would be a bit more complex. And that's usually if you start developing with using a mutex, well, it's not that complex, and you will not get maybe the performances you expect. You will not multiply your performances by your number of cores, but it's a start, and you will go probably faster than conventional code. So we have actually several components that are available with a parallel implementation, and this is a pending PR that will analyze your scene and suggest changes in your scene. So, for example, it will see that you use hexahedron FEM force field, but there is a parallel implementation called parallel hexahedron FEM force field, and it's up to you to replace it. So yeah, a pending PR that suggests you to use a parallel implementation. So I hope that you will use it, but for that you need to compile the multi-threading plugin. Okay, so that was for the CPU parallelism, and now I want a quick word on CUDA. CUDA, it's the framework to execute code on the GPU, on NVIDIA GPUs. So we have two plugins that are able to execute code on CUDA. The first one is SOFA CUDA, it's shipped with SOFA in the source. It's not compiled by default. You have to compile it by yourself. It only depends on the CUDA framework that you have to install. So it will compile a list of components that are the same than the ones that are in SOFA, but with a different template. So you need to change a bit your scene and have only CUDA compatible components in your scene. Yeah. And the second plugin is SOFA CUDA Linear Solver. It has been developed in the team by a former intern. This is basically one component that is a direct linear solver. And it's based on a CUDA library. And it's compatible with any scene written, even for CPU's scene. So you don't have to have SOFA CUDA in order to use this library. And Hugo, you said it, it won the SOFA award last year. And it's suitable for very large systems. So yeah, the parallelism is not that great. So you really need to have very large systems so that you can benefit from performance improvement. And the last type of parallelism that you can have is with SOFA Launcher. It allows to run multiple simulations in parallel. It's a Python script that is shipped with SOFA, and multiple simulation in this case means that we have multiple instances would execute a local machine or on a cluster. That was it about parallelism in SOFA. Any question?
Thank you, Alex. Thank you very much. No, I was wondering if finally we have a version of a parallel version of the Ghost Sidle.
Not yet.
And a parallel version of LLT.
No, because I remember that at some point we discussed about that, but I don't remember if there was a version.
Yeah, not yet.
Not yet.
But now that we have the tools that I have presented, it will be easier to write it.
Okay.
Because yeah, so before the introduction of the two functions that I introduced here, was quite a pain to write parallel code in SOFA.
Efficient parallel code.
Efficient parallel code. No, even not efficient. So yeah, so what I presented here, the simplest example here, was not possible because here I present this example with a lambda function that is quite simple to. When you know what a lambda is, it's really basic to write this code. But before last year, I think, or at least several months, it was not possible to add a lambda function to the task scheduler. You needed to create classes and instantiate this class, create special constructors so that you can capture some parameter, etc. So it was quite complex, and it was frankly not motivating to create all this or to write all this boilerplate code. Compared to here, you just need to write a lambda, and you know exactly there is a proper syntax to capture the parameters. So yeah, it's really makes things easier to write parallel code. So I would say the ability to use lambda functions and the two functions I introduced.
Okay, great. Quentin?
Thank you for the whole presentation. It's good to have another view of what we can do or what is in development. I just had a question about maybe one comment that was given by Hugo, I guess, at some point. You are working on. You said you are working on domain. Not discretization, but working on subdomains, correct?
Domain decomposition. Yeah.
Domain decomposition. Is it a question of having a FEM model and computing several regions in parallel to do this, or this has nothing to do with
Yeah,
this?
it's so what I showed here. What I show here is quite a naive implementation where I use mutex to synchronize threads because we have a data race.
Okay.
And with FEM, usually you will have data race, and you don't have any opportunities, or it's not trivially parallelizable. So you need to find other IDs. So this is a naive example, naive implementation, but a more advanced one is to decompose your domain, your mesh in different domains and compute them in parallel. And once you have done that, you need to assemble the borders between the domains.
Okay. Yeah, that doesn't sound easy, but it's pretty cool. I mean, yeah, it's like not having one thread by elements, but it's considering like limited number of threads for limited number of regions. Sounds cool. Okay.
If you decompose your domain, you are sure that if you are writing a force on your domain, it is not possible that another thread is doing the same thing on the same element.
Yeah, so you manage better
That's a way to avoid the data race and to avoid also expensive mutex acquisition.
Okay. Thank you.
Any other question? Mr. Tallo.
Yeah, well, maybe last one for me. It would be a more generic question, Alex. How do you see the what should be the way? Should we go
this
like
is the way?
Yeah, exactly. But what is this? Would that be rather CUDA, according to you? Regarding, I would say, for an open source project like SOFA to remain pretty generic and to bring the most increase of performances, would you advise to go more for parallel using a multi-threading or CUDA, or a mix of both, or a CUDA for solvers and parallelism on another stage? Yeah.
It really depends on your application. Yeah, so I don't know, maybe you want to compute I don't know, a learning algorithm on a cluster and you don't have a GPU, of course, you will need a multi-threaded implementation. And maybe you don't have an NVIDIA GPU on your computer. You have a AMD one, and you are screwed. You cannot use a SOFA CUDA. And if you have a multiple core CPU and NVIDIA GPU, the best that you can do is even use a hybrid approach where you compute things in parallel on your CPU while you are computing things in parallel on the GPU. So you don't spend, so all your resources are spent optimally. That is the optimal way.
I remember doing that for the simulator years ago with Federico. He mentioned like the fact that we needed to have like a specific thread that would like discuss and interact with the GPU to make sure that you always have this safe thread dedicated to GPU communication somehow, like triggering the kernels. But in that case, what would be on the GPU? What should remain on the CPU? What's your opinion on
yeah, the perfect example would be, I don't know if it's possible now with SOFA, but this is what I presented with the free motion renovation loop. You have two threads. One is computing the free motion and one is computing the collision detection. And each of these threads is calling something on the GPU. So now it depends on your GPU. If you have a very powerful GPU, it could maybe handle both on the same GPU. Otherwise, it would need to wait that one kernel is over. But you can also have two GPUs. One is computing the free motion and one is computing the collision detection, but you will have the problem that you need to share data between GPUs and with the CPU. So this could be beneficial only for very large systems, probably.
So since we are recording it, and maybe if you agree with that, I would like upload the video, the recording on YouTube, since it seems to be mostly like based on the open source code base of SOFA. But to make like a summary, it will be first to any of you use it, right? You can use those code as soon as you want to accelerate your simulation. It would also give feedback. It would allow to give feedback to Alex and basically all of us from the SOFA community. We have always, when we're using it, we have to be aware that it depends on, I mean, performances result will depend on what you are actually doing. And therefore, to assess what's the best approach, you have first to think about what you are actually simulating to distribute at best the computational power, and to then test it and benchmark it, I guess, using the potentially very interesting plugin that you did, SOFA benchmark. But, would that be correct to say that?
For a specific simulation, I would use only the tools that are already available in SOFA, so using the advanced timers and simply the final timings at the end of a simulation that gives you the FPS. Because SOFA benchmark is only for micro benchmarking. So let's say I want to write a C++ code that compute the product of two small matrices. I will use the SOFA benchmark. but not if I want to compare the same scene but with different components that will accelerate potentially the simulation.
Thanks a lot, Alex.
But you are right that you need to profile, or at least to compare the performances between two designs of scenes, because there is no way that there is an automatic analysis of your scene that will suggest how to do better. I mean, I presented one here that suggests to use a parallel implementation when there is one, but it does not mean that this parallel implementation will be suitable for your case. It's just a suggestion, and you have to test it by yourself. And this is the same for CUDA. You need to test it.
Okay, thank you very much.